Hi, David.
Hello, good morning.
Good morning. All right, so today I'm going to solve some examples on the impulse and momentum of rigid bodies. And I think today will be the last official lecture in the dynamics class. So this will be like just applications, all the content is done. And the final exam will be based on all the content since June 14th up today. So all the lectures here on our YouTube channel. So I think we have from lecture 1 up to lecture of today, which will be 32. So this is all the content that we covered for dynamics. And if we are talking in terms of chapters, so in Hebler textbook, so for Hebler textbook, we cover these chapters from chapter 12 up to chapter 19. However, there's some topics within these chapters that hasn't been covered, but you are responsible of everything that has been taken in the class. Like we take from chapter 12 here, kinematics of particles, up to chapter 19. And we will not do chapter 20, 21, 22. So this will be up to chapter 19. And be careful because there are some topics, maybe within any of these is not like the central force motion. We didn't cover this. So just like you are responsible of the content on the channel here, and also you can access this from the modules. So you will find each module and the homework associated with each module. So this is all the content that we covered. Okay, so let's start today with solving some examples on the concept of impulse and momentum and end this chapter. So our first example is that we have a disk, and this disk or a wheel moving on the ground like this, and we have cable at this point, and the force in this cable is equal to 10 plus t, so it's function of time, and this is in ton, or I think Newton. Yeah, let's make it Newton. So let's call this B, and the disk has like two radiuses. So this is the first one is 0.4 meter, and the second one is 0.75 meter. So you are given that the mass of this disk is 100 kilogram, and the radius of gyration is equal to 0.35 meter. And you know that you can use this piece of information to get the moment of inertia. And you're also given that B is equal 10 plus T Newton. And this disk or this spool starts from rest and you are required to get the angular velocity, at t equal 5 seconds. So the first thing I will use this piece of information to get I. This is what I will do first. So I is equal to the mass multiplied by kg square, and the mass is 100, and multiplied by 0.35 square, and this should give you 12.25 kilogram meter squared. So that's what I would do first. The second, to solve any impulse momentum equation, you will have to draw a free body diagram and a kinetic diagram. So let's make it here. We know that the free body diagram would put all the forces on the body. So let's see what forces we have here. All right, so assume that this is the ground. We have B equal 10 plus T, and we should have weight is going down, and we should have a reaction in here, and it should be a friction force. So let's assume that with this B, this body is going to make an omega in this direction, and it's going to move in this direction. So we will have, when we are dealing with forces and in a chapter 17, we put here MA, but right now we are dealing with impulse and momentum. And for impulse and momentum, we are caring about the linear and angular momentum. So the kinetic diagram will be the mass multiplied by V at the CG, not the mass multiplied by the acceleration. And the second thing is the I bar omega, because this is the main elements that we need for the angular momentum and linear momentum. So that's the two components that we need. All right, so with this, let's assume the friction in any direction. So you are not like obliged to check a specific direction. You might choose, like, I assume that the omega in this way, but it will not be in this way. So it will be negative. That means that your assumption is wrong and it's in opposite direction. So I can assume that the F of friction is in this way, and if it's not, it will be negative, and that means it's in opposite direction. Okay, so right now we have all the forces here. So let's start the angular momentum equations. So this is a general plane motion. Why? Because this body is rotating and translating. So we can use our three equations of angular momentum. I think we have them somewhere here. Yeah, there's three equations, one in X and one in Y and one in K hat. So X and Y is very simple, but the angular momentum one, you are allowed to use the angular momentum at any point on the body, at the CG, at the instantaneous center, at O, but just to choose the point that will make your problem more easier. Okay, so let's start by, okay, we know that this body will never move in the Y direction. It always move in the X direction. So we don't have to construct an equation in Y direction because we know that all the terms will be equal to 0, but we can do it. I mean, like the velocity terms, but you might get like some results out of this equation. Okay, so let's start our first equation, number 1, and let's do the X direction. So for the X direction, we will have mv bar in the X direction plus the integration from T1 to T2 of all the forces dt, and this forces should be in X direction, and this will be equal to mvx2 bar. And let's assume a positive direction. So I will assume that the positive X direction is in this way. Okay, so from this piece of information, the spool starts from rest. That means that the initial velocity is equal to 0. So this term will be equal to 0. And let's get the second terms. So let's see what the forces that we have in X direction. So we will have this friction F and this B. So let's integrate this part. So we have 10 plus T in the positive direction. And this will be integrated with T, so we'll have dt here. And actually we can put them, all of them, and then okay, let's put number 1, 10 plus T is positive, and we will have negative F friction. And let's call this point A, so we will have FA and NA. And all of these will be integrated with respect to t, and we will integrate from rest at time 0 up to 5 seconds. And this should be equal to the mass, which is 100 kilogram, multiplied by Vx2 bar. All right, so what's required here is the angular velocity. So we need to transfer Vx into omega form. So if we have this, and we have the center, and we know that there is a Vx bar is here. If we want to get the Vx bar in terms of omega, and we know that the omega will be in this direction, and here is an instantaneous center of zero velocity, and this is r, so Vx bar is equal to omega multiplied by r. So omega will be equal to Vx bar over r, and we know the radius is given in the problem. It's equal to 0.75. So this is equal 0.75 omega, and also Vx bar here over 0.75. So we can remove Vx2 and put 0.75 omega 2. Okay, so let's integrate this first, the left-hand side. So we will have 10t, if we integrated this, plus t squared over 2, and minus fa t, and all of these will be substituted from the upper and lower bound of the integration, and this should be equal 100 multiplied by Vx2, which is the 0.75 omega, and this should be omega 2. Okay, so if we have this, so we'll have 10 multiplied by 5 plus 5 squared over 2 minus fa multiplied by 5 will be equal to 75 multiplied by omega 2. So this is a single equation, function in fa and omega, and after some mass, we will have that fa will be equal to 12.5 minus 15 omega 2. All right, so 15 omega 2. So we got our verse equation. If you want to try the second equation in y direction, so number 2, let's make the positive in this way, and let's try mvy bar plus the integration from t1 to t2, all the forces in the y direction is equal to, this is y1 mv y bar 2. As we know, there's not any movement in the y direction, either at 1 and 2, because this will be moving this way. So this integration will be equal to 0. So we will have the forces in the y, we have weight in negative y, and we have n in positive y. So it will be the normal force minus the weight integrated from 0 up to 5 equal to 0. And this will give you that the normal force is equal to the weight, which is 100 multiplied by 9.81. So it's 981 Newton. So we got the normal force. Number 3, which is the most interesting one, which is the moment. So let's see what is the more easier to do here. Is it more easier to take the moment here or take the moment here, and why? Does anybody know? So this is the CG, and this is the instantaneous center of zero velocity. Which one is better to take the moment about? Does anybody know?
Wouldn't it be the instantaneous center?
Why?
Because a bunch of points are, a bunch of forces are going directly to it, so they don't generate moment.
Exactly. that because if I take the moment about point A, so the weight is passing with A, the normal force passing with A, and F is passing with, so all these forces will have zero moment, and this will leave us with only B is causing moment. So this will be much more easier to do. So I can write my equation and have the moment about the instantaneous center. And let's make the positive direction. So let's pick a 1. So let's make this is the positive direction. And this will give us the equation that the I at the instantaneous center multiplied by omega 1 plus the integration from T1 to T2 of some of the moments about the instantaneous center integrated with respect to T will be equal to the I at the instantaneous center multiplied by omega 2. So this is our equation. If you will take the moment about this point, the CG, so it will be the same equation, but you will change the I to be the I bar or the I at the CG, and the moments will be the moments of all the forces about the CG. Okay, so omega 1 is equal to 0 because it's starting from rest. And let's get the moments. So we only have one force, which is P, sorry, it's 10 plus T. Let's put it direct. So it will 10 plus T multiplied by 0.75 plus 0.4. Why? Because if I'm taking the moment about this point, so I need to account for this arm, and this arm is equal to the big radius 0.75 and the small radius 0.4. So this is the arm of this force, and I need to integrate this with respect to dt from 0 to 5, and this should be equal to the moment of inertia about the instantaneous center, and this is equal to the moment at the CG plus the mass multiplied by d squared. So I need to transfer the moment of inertia from the center of mass to this point. So what I will do, I will get the moment of inertia about the CG and then multiply the entire mass by this distance d, which is 0.75 squared. Okay, so we have I bar, it was equal to, let's put this is I bar plus m d squared multiplied by omega 2, and I bar was 12.25, and we have the masses given 100 kilogram multiplied by 0.75 square, and all of these is multiplied by omega 2. And when we integrate this equation, it should give us, so this will be like 1.15, 0.4 plus 1.7, so this will be 1.15 10t plus t squared over 2, and I'll substitute from 0 up to 5, and here it should give us something in omega 2, and after you substitute all of these, this term will be 71.875, and you will have other term here, and this should give you that omega 2 is equal to 1.05. And if it's required in this problem to get the friction force, so you will substitute with the omega here and get the friction force. So this is how you solve the problem. If I were you and it's only required to get the angular velocity, I would start with the third equation and I directly get the omega 2 just from these 3 steps, and I don't have to do the x and y direction just in case if it was asked for the friction or the normal force, so I will do the other 2 equations. But if it's not, I would save my time and go directly to equation number 3. Does anybody have any question on this problem? Okay, so let's solve a problem that has 2 bodies. Example 2. Let's assume that we have a desk here and it spins. There's a pin here, and the radius is 0.2 meter. And we have a weight attached to a cable, and this weight is 6 kilograms. All right, so let's call this body A, and this will be body B. And body A has a weight of 20 kilograms. And at the initial state of this system, this weight was moving with 2 meters per second. So this is VB is moving down, and you are given in this problem that IA, the moment of inertia of the disk, is equal to 0.4 kilogram meter square. Okay, so this body, it doesn't have a moment of inertia. We will deal with the body B as a particle, but because it doesn't rotate or it doesn't, the inertia is not important for this body, but we have a disk and the inertia is important. So it's 0.4 kilogram, and you are required to determine VB after 3 seconds. So we need to determine the velocity of the body B after 3 seconds from this instant. Okay, so there are two ways to solve this problem. You can solve it as a system, or you can separate this system into two systems. So if you solve it as a one system, so you will only have the VB and you have the mass of this body, and then start solving this as a system. But if you want to solve it as a two bodies, as a separate system, you will have to cut here. To cut at this. And when you cut this cable, the tension in this cable will appear. So let's see how can we solve this as a two bodies. All right, so if I solve it as a two bodies, I will have my disk here, and I'll have my weight somewhere here. So this will be for the free body diagram, and the second one will be for the kinetic diagram. Okay. So let's see what is the forces that we have here. We know there is a pin here. So whenever I have pin, I should put reactions. So let's call this pin A. So I will have AX, reaction in the X direction, and reaction in the Y direction. We have the weight of this body is going down, and we have a tension in the cable like this. So you will have to put all the forces so you can get your problem solution correctly. And you will have another, on the other body, you will have the tension here because we cut here. When we cut here, the tension in these two bodies will appear, and you will have the weight. So let's call this is weight of body A, and this is the weight of body B. So we put all the forces on the two bodies, and let's go to the other body. Let's see the motion. So the motion for the body A, it only make rotation, and this will be something like that. So it doesn't make any translation in X and Y direction at this point. So this point is restrained from moving. We have I bar multiplied by omega. And the body B, let's see what is the motion. It's only making linear motion, and it's moving down VB like this. So I know the motion of body A and body B. I know all the forces on body A and body B. So let's start do the impulse and momentum for these two bodies. So let's start with body, this one. So let's call this is 1, and this is 2. And actually we have A and B. We can use A and B. So here is A and here is B. So let's start here. Four, body B. For body B, I know there's not any angular momentum because this body is making vertical movement, and there's not X linear momentum because this body is moving in the Y direction. So what I will do, I will get in Y direction. So let's say here in Y, and I'll make the positive is going up. So our equation will be mvy1 plus the integration of fy dt from t1 to t2 equal to mvy2. All right, so we actually vy1 is not equal to 0, it's equal to 2 meters per second. So we have a 1 and it's going down, and we have our positive is going up. So, and the mass is 6 kilograms for this body. So we will have negative 6 multiplied by the vy1, it's 2 meters per second. So we got it here. And plus Fy, so the forces in the Y direction, we have T in the positive direction and weight in the negative direction. So we'll integrate from T1 to T2. T positive minus the weight, which will be 6 multiplied by 9.81 dt, and this should be equal to the mass, which is 6 kilograms multiplied by Vy2. So I will have to assume a direction of Vy2. So we can assume it in the negative and see if this assumption is right or wrong. So we will assume it's going down. So this will be negative Vy2, something like that. And this will be negative 12 plus the integration. So we will have T, and we have actually T1 is equal to 0 and T2 is equal to 3. So this will be T multiplied by 3 minus 6 multiplied by 9.81 multiplied by 3. And this will be negative 6 multiplied by Vy2. So this is an equation in two unknowns, T and Vy2. There's no square here. And when you did the mass, you will find that 3T plus 6 Vy2 will be equal to 188.58. We got equation 1. So let's get the second equation from the other body. Okay, let's write here for body A. And for body A, we will only do the angular momentum equation because we know that this body is not moving in X or Y direction. So let's start with the angular momentum equation, and let's assume that the positive direction is in this way. So we will have the I about the CG multiplied by omega 1 plus the integration from T1 to T2 of the moments about the CG, let's call it G dt, will be equal to I bar multiplied by omega 2. Okay, I bar is given, I think it's 0.4 kilogram, and this is about the CG. And the moment about the CG, if we take the moment about the CG, the reactions will be canceled and also the weight, and we will leave us with the T, and the arm of this T is 0.2, which is the radius of the circle that is given here. So this will be equal 0.2 T, and it's starting from rest, so this will be equal to 0. Oh, it's not rest, sorry. It's the VB initial has 2 meters per second. Okay, actually we can transform VB into omega. So if we have this body and we know the V at all of this cable here is equal to 2 meters per second. And we know that this is the R. So we know the V at this point. So the omega, or we can say that V is equal to omega multiplied by R. So omega will be equal V over R. And this will be V over 0.2. And this will give us 5V. So the omega of the body B, or sorry, this will be body A because body B is not rotating. All right, the omega of A will be equal to 5V. So if we want the omega A, 1, so it will be 5 multiplied by 1 multiplied by 2 meter per second. So it's given here. So it will be 10 radian per second. And if we need omega 2, so it will be 5 multiplied by V2, which we don't know. So let's substitute here. So we have I bar is equal to 0.4 multiplied by omega 1, which is 10. This will be plus the moments. So the only force that make moments is the tension multiplied by 0.2. So don't forget the moment arm. So T multiplied by 0.2, and this will be integrated from T1 to T2, which is 3 minus 0. And this should be equal to I bar, which is 0.4 multiplied by omega 2, which is 5 multiplied by V2. So we will get another equation in terms of T and V. So this equation will be 0.6 T if you multiply 0.2 by 3, and minus 2 V2 if you multiply 0.4 by 5 will give you 2 V2, and make it in the other side will give you negative. And this should be equal to negative 4. So this is our second equation. If you solve this two equations, you will have that Vy at the second after 3 seconds, it will be 13.036 meter per second, and T will be equal to 36.78 Newton. So we got all the information of this problem, and what is required is VB after 3 seconds, which is VB2 here. All right, does anybody have any question on this problem? All right, so let's solve another problem, and it's a similar to this one, but it's a little bit different, and we will solve it using system approach, not separating the bodies like into two rigid bodies. Okay, so let's solve example. Okay, so we have a pulley like this, and we have a cable attached here, and this cable is come all the way here, and there's a force. Here is 380 Newton, and there is a weight coming down from here, and this weight is 40 kilograms. All right, so this is body A, and this is body B, and the body A has a weight of 30 kilogram, and the radius of this body is 0.35 meters. So you are given in this problem that the radius of gyration of this disc or this pulley is 0.25 meter, and it's given the mass here. The mass is 30 kilograms, so you can get the I, and the Boolean mass. So these two bodies have an initial velocity of 1.2 meter per second, because if this pulley is moving down, this mass will be moving down with the same velocity. So the pulley and mass has V1 1.2 meter per second. So it doesn't start from rest. And the force, this one, the 380 Newton, acted for 5 seconds. So it has an impulse, force multiplied by time, and this impulse time was 5 seconds. And what's required in this problem is to find the angular velocity and the tension in the cable. Find omega after 5 seconds and tension cable. This one, the tension here. Okay, so let's solve this problem as a system. So if we are solving this problem as a system, so we will not cut here. So the tension in this cable will not appear. So, but if you will divide it in two bodies, you will have to cut here and the tension will appear here and here. But if you solve it as a system, you will have tension from here and tension from there, and they will cancel each other. So this is as a one system. Okay, so let's put our system here. Let's see what we have in terms of forces. We will have tension in this cable, and we have force of 380 Newton, and we have the weight of the pulley, which will be 30 multiplied by 9.81, weight A, and we have another weight down here, weight B, and this will be equal 40 multiplied by 9.81. So this is all the forces that we have. Let's see the velocities. Okay. Right. So this pulley is allowed to move in the vertical direction, and as a result, the mass B will move as well with the same velocity. So if pulley 1 is moving down V1, this mass will be moving V1. So the mass V1 will be making a pure translational motion, but the pulley here is making translation, and actually it needs to do rotation to make this translation. So it's a general plane motion for this pulley. And we know from this setting that this location is an instantaneous center of zero velocity for this pulley. So we know that this is an instantaneous center of zero velocity. Okay, so let's solve the system. Solution using system approach. Okay, so let's just set up the equation that we need to have it here. So the impulse momentum equation, and I think we will only need the impulse momentum equation, and we will not need maybe in the end we will need the because here we know that we have three equations, one in X and one in Y, and one is the moment. And we know that this body is not moving in X direction. This will leave us with two equations, the moment and Y direction. So let's do the moment first. For the moment, we will get the sum of the I multiplied by omega 1. So the inertia of this system multiplied by omega 1. And I will take the moment about the instantaneous center of zero velocity. So I will need to transfer from here and get here. So this, to do this, it will be equal as, let's see from previous lectures. Yeah, that's Yeah, that's what we do. If we want to transfer from G to any point, either this point is A or the instantaneous center, we multiply I par by omega and then multiply D by MV. Or if we want to do the vector one, so we will have all of these and vectors, and then we get like, this is the CG, and this is the point that we want to get the moment about. So what we will do is that we get RG with respect to A and multiply cross product by the velocity at the center of mass. And that's what we are going to do here. All right, so we will have I bar, and this is at the CG, and this will be plus RG with respect to the instantaneous center, and this is vector crossed by the mass multiplied by V1 at the CG. Will be something like this. So this is H1, so let's put it here, H1 plus the integration of the moment dt from T1 to T2 will be equal to H2. So this is H1, and the second part of the equation is the integration from T1 to T2 of all the moments about the instantaneous center dt, and this should be equal to the sum of the I bar multiplied by omega 2 plus RG with respect to the instantaneous center crossed by MV2 bar. This is H1, and this is H2. Okay, so it will be a long equation, but we can do it. Okay, so we need to get I bar, and we need to see if we can get omega 1 or omega 2. So I bar will be, actually we can get it from here. We have the mass, we have K, so I bar will be equal to M multiplied by kg square, and this is 30 multiplied by 0.25 square. So this will be equal to 1.875 kilogram meter square. We got I bar. And we can get omega from the velocity. We can get omega in terms of the velocity. So we know that V is equal to omega multiplied by R if we know where is the instantaneous center of zero velocity. So let's do it here. We know that this body is making V1 is equal to 1.2 meter per second. So this body will have another V1, which is equal 1.2 meter per second. And we know that this is an instantaneous center, which this is R. And we know that there is an omega here. So V1 will be equal to omega multiplied by R. And this can give us that omega 1 is equal to V1 divided by R, and V1 is 1.2, and the R is 0.375. And this will give us that omega 1 is 3.2 radian per second. So we got omega 1 from the velocity, and omega 2 will be equal to V2 over 0.375, and this should be equal to, so V2 will be equal to 0.375 omega 2, because we don't know omega 2 and V2 as well. Okay, so let's see how can we substitute in this equation. We just got the I bar, and the I is the I of only the pulley, because this is the only body that is rotating. But the body B, so this is A and this is B. Body B is just moving, is not making any rotation. So we will have I bar of, it's 1.185, oh, sorry, 1.875 multiplied by omega 1. And let's be careful about the direction. Let's see what is the direction of the omegas. If this body is moving V1 down, so it will making, if you use your right hand rule, you will find that the direction of the omega is negative. And we just got the value or the magnitude of the omega 3.2. So it will be negative 3.2 in the k hat direction. So it has a magnitude 3.2, but in the negative k hat direction. All right, so we are done with the first term. Let's get to the second term, plus RG with respect to the instantaneous center. It will be this one. This is RG with respect to the instantaneous center. It has a value of the radius of 0.375, but let's see what is the direction of this cross product. We have, let's put it here. We are crossing RG with respect to the instantaneous center by MV1 bar vector. So we know that this is the direction of the R and this is the direction of the V. If you did a cross product of these two using the right hand rule, you will find that the resultant should be perpendicular on these two vectors, and it will have a negative k hat direction. So what I can do now is that multiplying them as a quantities, and I already know the direction will be negative. So I don't have to do multiple cross product. If you are confused, you construct the determinant of the cross product and do this multiplication. But right now, I'm pretty sure that it has a negative direction, and now I can multiply the quantities. R is 0.375 multiplied by the mass, which is, okay, so the mass is another issue. So what is the masses that are moving with V1? So the masses that are moving with V1 is this mass and this mass, the mass of A and mass of B. So I will have to put all the masses that are moving with V1. So this will be equal to 30 plus 40, the mass of the pulley plus the mass of the weight, multiplied by V1, and V1 is equal to 1.2. And I didn't put any direction because I already did the cross product here. I know that this is the direction of R and this is the direction of V. Then using the right hand rule, I knew that they are negative. Or you can have R is in the I hat direction, and you know it's a 0.375 in the I hat, and multiply this by M multiplied by V1, and V1 is going down. So V1 is 1.2 in the negative j hat direction. So if you multiply I, j, k, if you multiply I by j, it will give you positive k, but you have negative here, so it will give you negative k hat. And then you multiply the quantities. So either is fine. Okay, so we are done with this term, but don't forget to put all the masses that are moving with the velocity v1. And then the second term, the sum of the moments about the instantaneous center. So the moments about the instantaneous center, if I'm taking the moment, sorry, I will be taking the moment here. So I will have this, and this, three forces. So let's get all of their moments, and I should include the direction. So the weights WA and WB are making negative moment because it will be in the negative k hat direction from the right hand rule. But the 380 Newton here is making positive moment. If you use your right hand rule, it will be positive. So let's put the moments here. So you will have, let's have this negative 30 plus 40 multiplied by 9.81. So this is weight. I need to multiply by this arm, which is 0.375. So now I got moment. I need to integrate this moment with respect to t, and this is a constant force. So I multiply directly by the time. So I have 5 seconds and it's starting from 0. So it will be multiplied by 5 minus 0. So here, this is force. And when you multiply it by this, it will give you moment. And when you multiply it by this, it will give you angular momentum. That's what I did. So we got only the weights. Let's get the 380 Newton. It has a positive value, 380 force multiplied by arm, and the arm will be 0.75 because it will be the full diameter of the circle. So it's a 0.375 plus 0.375, it will give you 0.75. So this is a moment, and then you multiply by time to get the angular momentum. And it has a positive direction because in the k-hat direction. Okay, so I'm done with the moment. Let's get the other term on the right-hand side. So I will delete these guys. All right, so this will be equal I bar, which is 1.875, multiplied by omega 2, which I don't know. And I'll assume that omega 2 is in the same direction, like. So this is omega 1, and I'll assume omega 2 is in the same direction, which will be negative. So negative omega 2 plus RG multiplied cross product by V2, and I will assume that the V2 is in the same direction. So this will give us negative cross product because we are doing the same thing but with different quantities. So this will be negative, and R is 0.375 multiplied by the mass, so it will be 30 plus 40 multiplied by V2, which we don't know, and we can substitute here with V2 equal to 0.375 omega 2. So now it's only one equation and one unknown, which is omega 2. So you will have to calculate all of these values and be careful about the signs. This is negative, and you have negative inside here, and this is negative here, and this is positive. There's negative into omega. So you will have to be careful because there's a lot of numbers. And when you calculate this, you will find that omega 2 is equal to negative 8.53. That means that the assumed direction of omega 2 is not right. It should be in the opposite direction. So it will be radian per second, and that means that omega 2 as a magnitude has 8.53 radian per second, and as a direction, it will be in this direction. And that makes sense because this system starts going down, and now we applied forces for 5 seconds. So maybe this pulley can go up, and when this pulley can go up, it will be rotating this way. And when you calculate omega 2, you will find that V2 should be equal by multiplying by using this equation, 0.375 omega 2, and this will give you negative 3.198 meter per second. And this means that V2 has a magnitude of 3.198 meter per second, but it's going up, not down. Means like this pulley will be going up. So we got the omega and we got the V's. So if we want to get the tension in the cable, so we need to construct another equation. So because we talked a moment about here, about this point, the tension were excluded from the moment equation. So if we wanted tension to appear, we need to take the moment about this center, which will be another very long equation. But I would recommend to do the linear momentum in the y direction. So apply linear momentum in y direction. And the y direction, we will have the sum of the masses because we are working with a system that move with velocity v1 plus the integration of fy dt will be equal to the sum of the masses multiplied by v2, and all of these is in the y direction, and let's assume the positive is going up. So the masses that are moving with v1, so it's the pulley and the weight, which is 30 plus 40 multiplied by v1. And actually we have v1 is going down, but our positive is going up. So we will put negative here, and we'll multiply by v, which is 1.2. Plus some of the forces in the y direction. So the forces in the y direction, we have T plus 380 going up, and we have the weights is going down. We have 30 kilogram and 40 kilogram. So it's a 70 kilogram going down. So let's put them here. So tension plus 380 minus 70 kilogram multiplied by 9.81 because I will transform from mass to weight. So this is forces, and let's multiply them by the time, which is 5 seconds. And this will be equal to all the masses multiplied by V2. And we just got V2, and we know it's going up. So I will put 3.198 here. So this is a single equation function in T, and finally you can get T, it will be 368 Newton. So we got the T. So this is how we solve this problem. It's just two equations, but the first one was a little big. Here's this equation, but anything, just like be careful about the signs, about the cross product, about constructing the entire equation for the system. And actually you can solve this system as parts. Like if you want, you can have this body, and you can have, there's a tension going down, and let's call it T2, and you have T1 here, and you have a weight 300, sorry, the force is 380 going up, and you have the weight of this body, W1. So we put all the forces for mass 1. So for number 2, you will have tension T2, and you will have weight W2, and then solve this as system 1 and system 2. And also if you want to draw the kinetic diagram, so this body is moving here, so you will have mv1 like this, and you will have I bar omega 1 like this. So this body is making general translation, and this body will be making pure translation like this. You will have mv1, and then solve the system from the up, and you will have another new unknown T2. It will appear from this. You will get two equations from here, one in the moment and one in the y direction, and you will get another equation from here with this unknown. So you can use the T2 that you got from here and apply it here. So this is how you solve the angular momentum of rigid bodies. Does anybody have any questions? All right, I know it looks like it has a lot of work, but just like if you a little focus and be organized, I think you will be able to get the solution right. All right, that's all for now, and we will be having our last quiz tomorrow, and I will be sending an announcement with the topics that this quiz will be covered, so you will be prepared very well. And tomorrow will be our last 30 minutes. I will just like give you some few tips, how to study for the exam, how to prepare for the exam, and also how to tackle the exam problems so you can get as much points as you can. All right, guys, if you don't have any questions, see you tomorrow.
Thank you very much. I'll see you tomorrow, Professor.